In volumetric analysis, finding the exact concentration of an unknown solution requires a precise reaction with a known standard. Today, we are determining the molarity and strength of an unknown potassium permanganate, or KMnO4, solution. To do this, we will titrate it against a standard m/20 mohr salt solution. By the end of this procedure, you will know exactly how to execute this specific redox titration, identify the precise colorimetric endpoint, and perform the calculations required to find the molarity and strength. We will be working with three main pieces of glassware: a burette, a pipette, and a conical flask. The chemical players are our KMnO4 titrant and our mohr salt analyte. Unlike acid-base titrations, we do not need to add an external chemical indicator. KMnO4 is a self-indicator. Its distinct purple color will serve as our visual cue when the reaction reaches completion. Executing this titration correctly demonstrates a firm grasp of redox reactions. It requires strict quantitative precision in the laboratory, where a single drop separates accurate data from a failed experiment. Step 1 is preparing the titrant. We start by washing the burette with distilled water, then rinsing it with a small amount of the KMnO4 solution. Once rinsed, we use a funnel to carefully fill the burette with KMnO4. Immediately remove the funnel after filling. If a leftover drop falls from the funnel during the experiment, it will ruin your volume readings. Next, drain a small amount of the liquid from the bottom nozzle to clear out any trapped air bubbles. Looking at this diagram, you see the burette setup. View the liquid level at eye level to prevent parallax error. Moving down to the conical flask, use a pipette to transfer exactly 20 milliliters of standard m/20 mohr salt solution into it. Before we can titrate, add roughly 10 to 15 milliliters, about 1 test tube's worth, of dilute sulfuric acid directly into the flask containing the mohr salt. This sulfuric acid serves two specific functions. It provides the required acidic medium for the redox reaction to proceed, and it actively prevents the hydrolysis of the ferrous ions present in the mohr salt. You must use dilute sulfuric acid for this step. Never substitute it with hydrochloric or nitric acid, as they are oxidizing agents themselves and will interfere with the KMnO4. Also, keep the flask at room temperature. Unlike the oxalic oxytitration, heating mohr salt causes the ferrous ions to oxidize prematurely. Strict adherence to these preparation steps eliminates invisible chemical interference. It guarantees that the volume of titrant you measure reacts strictly with the mohr salt, protecting the integrity of your final data. Place the conical flask on a white tile directly under the burette. The white background maximizes contrast, making the incoming color change much easier to spot. Now begin the titration. Open the stopcock to slowly release the KMnO4 into the flask, while using your other hand to continuously swirl the solution. Initially, the dark purple drops of KMnO4 will disappear the exact moment they hit the solution. This tells you the chemical reaction with the mohr salt is occurring rapidly. As the reaction nears completion, you will notice the purple drops taking slightly longer to fade. When this happens, slow the flow to a strict drop-by-drop pace to avoid overshooting the endpoint. Stop the flow when a single drop turns the solution a faint, pale pink. If this color persists for 30 seconds, you've reached your endpoint. If the solution turns dark magenta or deep pink, you have added too much titrant. That indicates an overshot endpoint, and the data for that run is invalid. You will need to start over. Identifying this faint pink threshold is the physical crux of volumetric analysis. It represents the exact moment chemical equivalence is achieved between the two solutions. With the endpoint reached, record your final burette reading. Subtract your initial reading from this final number to determine the exact volume of KMnO4 used. A single run isn't enough. You must repeat this entire titration process until you get concordant readings, meaning you record two identical final volumes in a row. This establishes your reliable volume variable, known as V. We can see the chemical mechanics on this worksheet. The net ionic equation shows the stoichiometric ratio of the reaction. This ratio gives us the core titration formula, connecting molarity, volume, and the N factor for both solutions. Set the unknown KMnO4 molarity times volume times N factor 5 equal to the mohr salt, molarity 0.05 times 20 milliliters times N factor 1. Solve for KMnO4 molarity without rounding. Finally, calculate strength by multiplying this exact molarity by 158. Through these calculations, physical observation successfully translates into precise, quantifiable chemical data. When documenting your work on a practical worksheet, ensure your observation table is complete. Clearly log your concordant readings and lay out your calculations for both molarity and strength. A successful result rests on 3 actions: preparing the apparatus without contamination or air bubbles, correctly stopping at the faint pale pink self-indicating endpoint, and applying the stoichiometric variables correctly in your math. Keep the core physical rules in mind. Read the meniscus at eye level, swirl continuously during the reaction, keep it at room temperature, do not heat it. Follow these steps carefully, and you will be able to execute this titration accurately. Good luck on your chemistry practicals. Mastering volumetric analysis develops the essential laboratory skills of precision, observation, and analytical deduction required for all future scientific endeavors.